Hello everyone. Today we'll talk about some of the algorithmic questions that have been recently gaining popularity in deep reinforcement learning. And what we'll talk today is sort of going to be a high level overview of some of the recent research trends in this area. And it'll be, in a sense, somewhat incomplete in that we'll not have answers to each question, but one of the primary goals today would also be to pose some of the questions which could be potentially very interesting research topics in and of themselves, as well as to discuss some recent research progress that has happened in the field of algorithm design for deep reinforcement learning algorithms. Okay, so broadly, what we'll discuss today is we'll see how whatever we have gone over so far, which is different RL algorithms as well as some of their theoretical aspects, how these kinds of things translate to practice. For instance, in deep Q learning, what are the kind of algorithmic decisions that we have seen in theory actually translate to in practice? So those kinds of things, we'll look at them. We'll also look at what phenomena happen in deep RL and how can we understand them. For instance, when we combine neural networks with reinforcement learning algorithms, do they behave in the same way as, let's say, a linear function approximator, or do we expect them to behave somewhat differently? So those kinds of things, we'll also discuss some of those phenomena. We'll also cover some of the aspects of what actually affects performance of deep reinforcement learning algorithms in practice, because in practice, deep neural networks are, let's say, are very good function approximators. So are the conventional issues that have been studied in theory, are those the things that affect performance, or are there some other issues behind deep RL algorithms that actually affect their performance? As well as we'll discuss some open questions that could potentially be interesting research topics in the space of algorithm design. And a short disclaimer here, which is that most of the material that we'll cover in this lecture is sort of very recent and still being actively researched upon. So I'll present some of my own perspectives on some questions in this lecture, but this is certainly not exhaustive in that I'm not going to cover everything or all of the recent directions in algorithm design. Neither am I going to cover different perspectives on the same problem, but I'll present some of my own perspectives and own thoughts on some of these issues. Okay, so let's start with Q-learning algorithms, so specifically deep Q-learning algorithms. So one of the most famous things, one of the most famous phenomena in Q-learning is this Ritz-Sutton's deadly triad. What that means is when you instantiate, or what does deadly triad say? It says that when you instantiate Q-learning algorithms, along with the combination of these three things, the triad, which is bootstrapping, which means you're trying to optimize a Q-learning objective that uses its own previous instance or its own generated target network to train the current instance of the network, which means you're bootstrapping, you're regressing to your own past self. Off policy sampling, which means the state action pairs are not drawn from the current policy's marginal distribution, but they're drawn from some other policy's distribution, which is what happens all the time because we use replay buffers, for instance. And when we use function approximation, which we use all the time because we cannot represent Q functions using tables because our state space is infinitely large. And when these three things are combined, what this deadly triad says is that divergence is bound to happen, which means these three things are a recipe for disaster in that the Q function can diverge and become super large, or it can take values that are basically kind of infinity. So this is what is kind of known, or it's been sort of one of the common things that have been looked upon when we talk about off-policy sampling and bootstrapping and function approximation. And it sort of affected the way in which we think about deep Q-learning algorithms, because then if this is true, we probably should not expect deep Q-learning algorithms to work in practice in a lot of the cases. So what we'll do is we'll kind of talk about some of these issues in this lecture and how they manifest in practice, especially with deep neural network function approximators. But before that, let's look at a simple example where actually this deadly triad comes into play. So there's this example, which is a two-state MDP, which is a counterexample proposed in this famous paper that is linked here. And in this MDP, what they're doing is they're parameterizing the value function of a particular state using a linear function. So it's basically saying I have some feature vector phi of s for each state that I know. And what I'm doing now is I'm parameterizing v of s as a linear transform of this phi of s, which is just equal to w times phi of s. So basically a linear transform. And if you do this, what tends to happen is that, and phi of s is 1 and 2 for the two states that you see there. And what tends to happen here is that you'll find that if you just do regular TD learning, things will diverge. So you'll get a W that actually grows as you train more. So if you see in the plot that is marked as subfigure B, you'll find that with more training, the vector W actually diverges and it becomes super large in magnitude. So what that tells us is that if you only have this one parameter to share, this W parameter shared across two states, you'll probably find that things will diverge and they'll give you poor solutions. And so in that sense, in like let's say in linear function approximation, if you do not have enough dimensions as a number of state action pairs, you might see divergence as well. But with deep networks, we know that we have so many parameters to model that we at least have we have parameters that are more than the size of the data set in a sense. So we have many parameters to some extent. And so what this example, the third part of this example, what it shows is that if you add in more parameters, for instance, if you add another free parameter, which is u here, you can find that things converge. So maybe they're not exactly right, maybe the solution is actually bad, but you'll not see unbounded divergence like what you're seeing in the B plot. So what this example really says here at a high level is that yes, divergence is common in these settings, but you can probably avoid them if you kind of manipulate your function approximator in the right way. So if you add another parameter, maybe you can avoid them. So what it says here is maybe more expressive function approximators can be better. It's not a proof that says more expressive function approximators would work, but you may be able to construct cases where that actually ends up working. So there's some hope for sure here. So there's some hope with regards to function approximation, and we'll discuss off policy sampling in a bit. So what all aspects we'll cover today with regards to sort of moving from the Q learning that has been studied in theory to deep Q learning in practice. We'll cover three aspects. The first aspect, which will be the stuff that we looked at briefly, which is the point about divergence. So divergence can happen when the deadly triad is satisfied, and a lot of the counterexamples have been developed where it actually diverges, where Q learning actually diverges. And there are several algorithms that have been tailored towards preventing this divergence, and a large part of the RL research has been towards this problem. But does it actually happen in practice, or do deep neural networks with the conventional techniques that we use, such as target networks, delayed targets, etc., do they already fix this issue? That's the first thing that we'll cover. The second thing that we'll cover is somewhat not directly tied to the deadly triad, although we'll look at one connection, which is this notion of overfitting or sampling error. So as with any learning problem, like supervised learning problems, etc., we would expect that when you train neural networks on a finite size data set, you would still suffer from some kind of overfitting, meaning that you would be good on the training data, but you may not generalize well. And where the definitions of generalize and being good on the training data are somewhat unclear in the Q-learning setup, but you broadly probably understand the point when you can draw a connection to supervised learning. So do Q-learning methods or deep Q-learning methods actually suffer from overfitting? That's the second question that we'll talk about. And here, in theory, we still know that there are worst case bounds, like you can bound the generalization of a neural network or by using sort of some theory. There's a lot of theory on generalization, but we don't know how we don't know how those things still behave in practice. There are still sort of bounds that we can get, but what is the exact behavior in practice? If I were to run Q-learning or deep Q-learning methods on my RL problem as a practitioner, I don't know what will happen. And the final bit that we'll talk about today is the notion of data distribution. So we've seen that the deadly triad, basically what it says is that if you have off-policy sampling, that's a recipe for disaster when combined with bootstrapping and function approximation. So maybe we shouldn't use off-policy sampling, we should use on-policy sampling, and maybe we don't even fall into that category and we'll be good. But we know that in supervised learning, if your data distribution is somewhat very skewed or narrow, in that, let's say you have a binary classification problem and you're classifying examples into class 1 and class 2, and out of 100, you have a data set of size 100, and out of those examples, 99 of the examples are all from class 1, and one of the example is from class 2. In that case, what you will end up finding is that training a neural network would give you kind of very biased solutions, because you have such a highly skewed data distribution which puts so much mass on 1 and not at all any mass on 2. So narrow data distributions are bad. However, if you think about an on-policy distribution, so let's assume there's this big MDP, and you're running this one single trajectory through your, or one deterministic policy is being executed through this MDP, you'll probably cover a very small area of this MDP, right? So you'll not be able to cover most of the MDP because a deterministic policy, let's say, will only go in very deterministic regions of the state space. So in that case, if you train under a non-policy distribution, you can imagine intuitively that there's a trade-off between sort of getting brittle solutions because you have a very narrow distribution here. Your Q function will not generalize, let's say, outside of this trajectory that you've seen. So that will happen. Whereas we know that with off-policy distributions, things can also go bad because off-policy distributions are figure themselves in the deadly triad. So there's still a trade-off. Like we don't really know whether on-policy distributions are really good. So which distributions are then good and how can we get those distributions? So that's sort of one more question that we'll talk about. And here too, we as we looked at in the offline RL lecture as well as in the RL theory lecture, you can prove worst case bounds. You can show that in the worst case, you need some properties on the data distribution because otherwise things will be bad. But how do things typically behave in practice? The average case scenario. That's sort of unclear, and we'll go over some of those things today. Okay, so let's start with the divergence bit, which we sort of had a little intro to at the beginning of this lecture. So divergence in deep Q learning. So turns out that when we actually train QLearning algorithms on, let's say, practical problems, we often typically find that with neural network Q functions, if the neural networks are large enough, you wouldn't really find a lot of divergence, but you would probably find a lot of overestimation. So the Q values would be overestimated a lot, but divergence may not happen too much. For instance, this paper from 2019, what it did was they basically took the suite of Atari games and they trained many different algorithms, as you see here, like the Q learning with regular Q functions, with target Q functions, with double Q learning, etc. And what they did here was on these Atari games, on an average, they measured how they plotted the magnitude of the Q values on the y-axis for the two plots that you see. And the x-axis they plotted the time, the number of frames you've seen. So this is the sort of the number of samples you've seen from the environment. And what they're plotting with multiple of these curves is they basically took they basically ran different games for multiple seeds. They took the values they basically at a given time step they basically accumulated the Q values across different of these runs, and what they did was they plotted the percentile, like different percentiles of this set of Q values you get over for each time step. So they plotted the 58th percentile, which is marked as 0.5, 75 percentile, which is marked as 0.75, 0.9, which is 90th, 95th, and 99th. And what they found in either case, or in all the cases almost, and this is averaged over all games, so they found in averaged over all Atari games that your performance or your Q function essentially sort of, even the worst case, which is 99th percentile, it goes up a lot large, so it becomes 10 to the 7, although the optimal Q function is sort of like, should be below 100 in this case, but it eventually comes back down. So it never really diverges in the way that we saw the counterexample diverging, where we saw literally a flat line that would go up and become super large. So in this sense, what it really tells us is that you can see a lot of overestimation, but maybe divergence does not really occur. And in particular, in this scenario, the authors did not find that divergence happens actually. So no divergence happens here really. It's pretty surprising in a sense because Atari is a complex domain. You have to learn from images, and you have to fit so many data points because you have a very big buffer and so on. But that's pretty interesting that divergence does not happen. We also tried a similar experiment in a paper that was concurrently published on a grid world domain. So what we did was we created this grid world, which is basically a 16 by 16 grid. And what you can do is you can an agent can navigate in this grid. So it can go front, it can go backwards, it can go left, right, or just stay at the current location. And there are walls in this grid world, and your task is to navigate to a certain location. So in that grid world domain, what we also found was that if you increase your network architecture a lot, you'll probably find that you can exactly fit you can exactly fit bell manners and so on. So you can basically exactly learn, and your returns would actually be high. So the error that you see in these plots, in the second plots, it basically decays down as your architecture size increases. For example, 256, 256, which is a two-layered network of size 256 each. The layer sizes are 256 each. that's kind of it kind of has a very low error as compared to 6464 or 1616 or 44. And in this case, what we found was that large neural networks just seem to be working fine in an FQI style setting as well as in the DQN style setting. And we only were able to sort of construct a case where divergence happens, but that was super infrequent. So it was 0.9% of the cases had divergence, and those were also cases where your Q network was very small. For instance, it had only two layers of 4 and 4 size each, which is in a sense very small because a conventional Q function networks have at least 256 size hidden layers and at least two of those layers. So in that sense, in a realistic sense, divergence is not a problem with deep Q learning in an online setting. So I would agree that in an offline setting, as we saw in some of the plots in a previous lecture, divergence can happen. But when you collect online data, so in all these settings, you're still collecting data online, divergence does not seem to be a big issue. Whereas in a more theoretical sense, divergence is still an issue on the online setting that when you collect data. Okay, so the first part basically told us that divergence, which is one of the primary things that has been studied, is probably sort of not a big issue with deep Q-learning algorithms. It's more like overestimation being an issue in there, and perhaps we need to fix for that. And we already looked at some of the fixes so far. For instance, we talked about double Q-learning and so on, and there are many other ways to tackle this. But those are potentially some interesting research directions as to how you can fix this behavior or why this behavior happens where Q values diverge up initially and they become super large and then they come back down. That's also a potentially interesting research question to explore as a separate question in itself. Okay, so the next part that I'll talk about is the part about overfitting or sampling error. So just like any other neural network training procedure, when you train on a bunch of samples, for instance, you want to minimize Bellman error or TD error here, but instead of having the true expectation, you have a sum over samples. So you have a dataset D, summing over it. The dataset D may not be a static dataset, it could be collected from your own policy, but you're still summing over it. And in this scenario, you can still overfit because you don't know the true expectation, you only have seen a bunch of finite number of samples. So does overfitting actually happen? So what we did here was we ran a small experiment on the same grid world domain that we discussed on the previous slide, where what we did was we varied the number of samples that were collected from each policy during during each iteration or each round of data collection, and we trained Q functions on that for equal number of gradient steps. So what we did here was we varied the number of samples we were adding to the replay buffer during training, and the different lines that you see on this plot are basically corresponding to different amounts of samples that are added to the replay buffer. What we found here was that fewer samples lead to poor performance. So if you see 32, that's the line at the bottom. 512, that's the line that quickly rises up and stays at the top. So what that indicates here is that if you definitely have more samples, that's a good thing to do because fewer samples, they lead to poor performance, indicating that you are not generalizing well enough. You are fitting your training data perhaps, but you're not generalizing well enough to the whole MDP to other states, and so you are poorly performing. Similarly, one more experiment that we did here to kind of see what really works is we basically did this scenario where now instead of collecting data, so when we collect data online, we only look at the recent most samples that are collected. So we discard the entire replay history. So there's a replay buffer, we clear it and we add new samples to it, train on those samples, then clear the replay buffer again, add more new samples, train on those samples, and so on. So we are not retaining the entire history that the agent has seen. So now the different numbers indicate how many samples we are adding in each of these runs, or each of the iterations of data collection, but we are not retaining the prior history in the replay buffer. And the line marked in purple, which says replay buffer, is the traditional replay buffer where we are actually storing all the samples that we have seen so far. So in this scenario, what is very interesting is that, first of all, as we saw in the first plot, fewer the number of samples you're training on leads to poor performance. So this figure, what it's plotting is it's plotting the validation error. So what is the validation error? It's the Bellman error or the TD error that you see on your slide, but evaluated on a set of state action pairs that are not seen during training. So it's in a sense a notion of a validation loss function for your training procedure for Bellman error. And in this case, I mean, it's sort of very intuitive that from the first plot, what it means here is that If you're overfitting, your validation error should be higher or should be larger, and you see that actually. So 32 samples, when you're likely to overfit more, your validation error is actually larger than, let's say, 64 samples or 256 samples or 1024 samples. But the bit that is the most interesting here, perhaps, is that when you employ a replay buffer that's storing all your past off policy samples, it actually prevents overfitting. It actually gives you a lower validation loss, even if the data was actually off policy data. So the data is not really an on policy data. The data that is given to you is not really on policy data, but it's off policy data. However, a replay buffer is very effective in preventing overfitting. So perhaps this is sort of one of, or partially kind of trying to get towards the answer of the question that we talked about at the very beginning, which is why do off-policy distributions still, why can off-policy distributions can still be okay? And perhaps the answer is that if you're not able to collect a lot of online data during training or on-policy data during training, a replay buffer can just give you more stability because it can prevent overfitting. It can reduce it can induce a bit of bias in your system, but it can reduce variance because you're not suffering from the fact that you are overfitting to a finite set of samples and leading to high variance solutions. So that's a potential usage of the replay buffer that could be interesting here. So what happens when we move from fitted queue iteration style algorithms to more DQN or actor critic style algorithms? So both of these plots that we talked about here are fitted queue iteration algorithms. So they're actually fixing the target value, training on the Bellman error until completion, then again fixing the target value, training until completion, and so on. So it's an ideal FQI algorithm. Now what happens when you do things with DQN or actor critic methods in here? So with DQN and actor critic methods, a more natural way to measure overfitting more natural way to measure how much you are training is this notion of gradient steps per environment step. So let's say you have an algorithm that looks something like this. You sample n samples from the environment. So by sample, I mean transitions. So let's say you unroll a policy, collect n many transitions from the environment. And now on these n samples, we train for k steps, or just on this n, or just on this data that is collected before collecting new samples from the environment. So what it's saying here is that for each sample that I collected from the environment, I'm training for k divided by n many gradient steps. So that's why k by n is gradient steps per environment step. So if I am if my k by n ratio is higher, that means for each effective sample that I got from the environment, I'm training more. If k by n is lower, that means for each sample I got from the environment, effectively I'm training less on that sample. So in this scenario, what happens is we again took the grid world example we have before, and we basically plotted this notion of performance as a function of how many gradient steps or how many effective gradient steps were taken per example or per sample in our data set, in our replay buffer. And this is all with the replay buffer scenario because we did not want to bring in on-policy distributions versus replay buffers because they can again be a little bit weird due to some other reasons because of on-policy, off-policy, etc. So we just did it with the same conditions or a replay buffer environment here. And what we find here is again that if you take more gradient steps, for example, the darkest line in this figure, which corresponds to 8 gradient steps, actually has a poor performance than, let's say, an intermediate value, let's say 1 or 2, and which is probably the best here. And the line which is sort of the least visible, or the line that is the thinnest line here, which corresponds to 0.5 gradient steps per sample, it's also good enough, although it's a bit slower during learning. So the trade-off here intuitively is that if you take enough number of gradient steps per environment step, you are kind of learning fine enough. If you take excessive number of gradient steps per environment, you are trying to learn a lot from your data, and because of the data being finite samples, you can overfit to them and lead to poor performance. So basically, there's a trade-off. Very few number of gradient steps implies you're not using them enough. A large number of gradient steps implies you're trying to use data too much. And a similar trend also holds true for Atari domains. So these two plots that you see on your screen are basically runs of a DQN algorithm in the online RL setting on the Asterix and Sequest games, which are two games in the Atari suite. And these three different lines that you see here are basically plotting the three different runs of a DQN algorithm for different numbers of gradient steps per environment step. So the red line that you see, which rises up the highest, basically corresponds to k by n equals 1. The blue line corresponds to k by n equals 4, which lies in between, and the orange line, which is the worst on all of them, corresponds to k by n equals 8 here. So basically what it says is that if you train more and more on your environment, you can lead to poor solutions, and those poor solutions sort of are more like overfitted solutions because you're training on the same data a lot more, and you don't want to do that. So all of this sort of says that yes, overfitting is potentially an issue and can lead to poor performance. So why does performance degrade with more training? So all of the things that we have seen so far have basically said that when you train more on the same data, performance can degrade. So why can the performance degrade with more training? So there are two possibilities or two answers to this question. The first answer is that there are large deep neural networks that we are trying to train. So the Q function is this big neural network that we are trying to train. And similar to supervised learning, if you train more on that Q function, you'll find that your performance degrades. So you get poor performance, and so more training would basically lead to more overfitting statistically and it'll be poor performance. The second possibility here could also be that the deep QLearning objective, which is this TD error objective where you're regressing to labels produced by your own previous target instance, that update is not typically the supervised learning update where you're trying to regress to a fixed label, right? So in a sense, what could be happening is there could be something else with the deep QLearning update function that might be making more training be less effective. So when you're training more on the same data, you might end up being less effective due to some other reason in this scenario. So these two possibilities, and which of these possibilities is actually true? So for the first possibility, we actually did a small experiment. What we did was we tried early stopping techniques. So one way to prevent overfitting in standard supervised learning is to figure out a place to stop training early. So you don't train too much, you just cut off training at the right location such that your solution is good enough and it is not overfit, but it's also trained enough so that it generalizes. And you use that solution and that's your final answer. That's your final network that you'd use on the training, on the test data. So can we devise, so what we did here, what we wanted to do in this experiment was, can we devise a simple sort of stopping mechanism or early stopping mechanism for Q learning? And now that's in itself a hard problem. So here in this figure, what we were interested in really was in some sense an oracle measure. So if I were given access to, let's say, even figure out in an oracle way, in a way that I could have access to privileged information, such as I could do rollouts in the environment, etc. If I can figure out in this oracle way when to stop, and that kind of oracle early stopping gives me benefits, then probably suggests that there is some contribution of the first possibility, which is that large neural networks overfit in the problem of in this whole problem with performance degrading with more training. So what we did here was we tried early stopping, and early stopping does actually help. So we tried two forms of early stopping that I'll discuss today. So the first form that you see, oracle returns. What we do now is for each of these, so if you remember from the previous slide, we are varying the number of gradient steps per environment step, right? So for each of these gradient steps, what we did here was we recorded or we stored the parameters of the Q function that we'll find. So we are basically maintaining everything into memory. And now what we wanted to do here was we wanted to see, we basically unrolled the argmax policy for each of these Q function checkpoints that we stored. So run the argmax policy in the environment. We figured out which of these checkpoints gave the highest return. So we use the environment as an oracle measure here because we are sort of querying the environment much more than what we are using it for. So we queried it much more, computed the returns for each of these samples, and figured out which Q function checkpoint gave us the largest return, and basically stopped training at that checkpoint. So in a sense, what we're doing is we ran training for many gradient steps, and then we figured out which checkpoint is the best, and we kind of assigned that as our final early stop solution, and then continue training from there. So it's sort of like, in a sense, it's almost like cheating, but we wanted to use like an oracle measure, and that's why we did this. The other measure that you see with the other line is basically sort of running again, doing this whole round of maintaining all the checkpoints that you observe with various gradient steps, and measuring the Bellman error in all of those checkpoints. But one catch here is that the Bellman error that we are doing here is measured on all states. So here we are assuming that we had access to all states of the MDP, and this is again on the tabular grid world, so we could do that. So we have access to all states on the MDP, and we are measuring the average Bellman error on all of them. Although we are training on only a finite set of samples and we don't have all the state action pairs given to us. So we assumed Oracle access to all states, we compared the Bellman error, and we picked the solution which has the minimum Bellman error in this sense. So it's in a sense sort of validation or cross-validation. And in both cases, what we found here, as you can see here, is that this can lead to about a 0.1 gain in normalized return. Both of these schemes are actually effective, which means early stopping is a part of the contributor here, or a part of the problem is actually overfitting. So is that all? Is possibility 2 not a big issue, or is possibility 2 is a big issue here? So it turns out that possibility 2 is also a major contributor towards bad solutions in QLearning algorithms. So why is that? So in a lot of these settings, performance depends on the fact that you're using you're optimizing a bootstrapped objective, which means that you're generating labels from your own past self for training your future self, meaning that you're training your future Q functions using past Q functions which come from the same network class, which were seen during the same optimization trajectory in the past, and those are being used for training. So basically, self-creating labels for training can hurt. That's sort of the main hypothesis here, which I'll present some evidence for. Before going down into the exact cause of these issues, let's sort of look at, or before trying to understand why self-training or self-creating labels and training on them can hurt, let's look at a little bit of preliminaries that will help us understand this better. So it turns out that that when you use deep neural networks, which have millions of parameters, and you try to train them on a dataset which is only 10,000 in size, gradient descent is not too bad. It actually does not give you solutions that overfit a lot. So why is that? It's because gradient descent has an implicit regularization effect in supervised learning, which means that if you have many parameters, or if you have many more parameters than how much data points you have, which means you're in an over-parameterized setting, you might end up finding that you will get a solution that is implicitly regularized in some way. You'll not just get any solution that satisfies that can predict that gets a zero training error on the trained data. To look at this, a simple example. Let's consider a simple example where, let's say, you want to find an x, which is your parameter, such that a times x is equal to y, or ax minus y's L2 norm squared is minimized. If you do gradient descent on this using a proper initialization, what ends up happening is you can show that, and this is shown in some of the papers that I've cited on this slide, you can show that the optimal solution to this problem, which gradient descent will find, is basically a solution which satisfies ax equals y, which means it gets zero training error. But it's also but among all those solutions that actually get ax equals y, this is the solution that is of minimum Frobenius norm. So Frobenius norm of x is actually very small. And here you consider x being x is a matrix. So what this tells us here is that gradient descent has an implicit regularization effect, which means that if you have limited data, it automatically adds sort of a regularization that can give you some sort of benefits here, because you're regularizing, so you may not overfit to them, or you may not just get any arbitrary solution, and therefore you might converge to a solution that has some nice properties. And if you're interested, you should also check out other papers on how this regularization effect is not as simple as just Frobenius norm in deep neural networks, but even when you have more layers in your deep neural network, you will get regularization that looks a lot like something like a rank regularization, where the rank of this matrix X would be small, or some notion of rank of this matrix X would be small. So there's a lot of discussion in there, and I'll skip that because that's not really the main point here. But sort of the high-level takeaway, which we'll use in the next slide, is that gradient descent in a supervised setting can lead to some sort of regularization on the network. So it will lead to regularization. It could be Frobenius norm. It could be rank-based regularization. It could be any other regularization, and so on. Okay, so what we discuss now is a phenomenon that we recently found in a paper that we did, which we called implicit underparameterization. So I'll provide a pictorial description of this, like a schematic, but That's on the next slide. But before that, let's first understand what exactly we mean by that. So when training Q functions with bootstrapping based objectives on a given dataset, so you have a fixed dataset, you are training Q functions using bootstrapping. Turns out that if you do more gradient steps for training, so here the data set is fixed, so you're not collecting any samples online. You're given your n is sort of fixed; it's given to you already, and here you're just doing more and more gradient updates on this data set. So it turns out more and more gradient updates leads to a loss of expressivity of the Q function network. And the reason for this loss of expressivity is due to excessive regularization. And this excessive regularization manifests as a loss of rank of the feature matrix. And I'll define all of these terms now. So just to parse it again, we are saying that when you're training Q functions on a given static dataset, more and more gradient steps leads to a loss of expressivity of the function approximator because of some sort of excessive regularization. And I'll define what loss of expressivity means, what excessive regularization means. And we're also talking about some notion of a feature matrix here whose rank is lost. So what are all of these terms? So let's imagine our Q function QSA is denoted by a neural network, which is given by a linear transform W transpose over a set of learned features phi. So your phi features, which maps state action pairs to a d-dimensional vector, are learned, and these are learned by a neural network that you're also training. And you have a W vector which belongs to R to the D that you're taking a dot product between W and phi to obtain the Q value for a particular state action pair. Now imagine the feature vector phi is decomposed as using its singular value decomposition as U times a diagonal matrix of singular values arranged in descending order times V transpose. So every matrix, every rectangular matrix will have a singular value decomposition that looks like U S V transpose, where S, or the diagonal matrix, corresponds to a matrix of singular values typically arranged in decreasing order, and U and V are orthonormal matrices. So this exists for every matrix. So let's assume that this matrix phi admits this singular value decomposition. Then, first of all, this matrix phi is the matrix that I refer to as the feature matrix in the statement above. So feature matrix is matrix phi. Now, what do we mean by the rank of this feature matrix? So what you can do now is you can define a surrogate or a continuous notion of rank of a matrix in terms of its singular values. So what is the rank? So rank is the number of effective vectors or effective number of elements in the space, or effective orthogonal elements in the space that is spanned by a particular matrix, spanned by columns of a particular matrix, right? So what you can figure out, or one way to define rank is basically to define it as the minimum number of singular components that can basically occupy more than a threshold, which is 1 minus delta mass of the total sum of singular values. So the singular value basically defines the strength of each particular sort of component of a matrix, or effective number of bases of a matrix. And the number of singular components that basically cover most of the mass of the total sum of singular values, which is shown in the denominator here, is essentially the sort of the effective rank of a matrix, because those many components are actually important for representing different features or mapping different state action pairs into a particular smaller space. But other than those, or other than k many components, may not be used, or may be used only a little bit. So S rank, which is the effective rank for a given threshold delta of the feature matrix phi, is defined as this expression, which is the number of singular values that capture more than 1 minus delta of the total sum of singular values. And we call it effective rank. So when I say a loss of rank of the feature matrix, I'm sort of referring to a loss or a decrease in S rank of phi over time. So basically one part of the statement is now clear, which means we now know how to define a loss of a rank of the feature matrix. So what is the other bit? So the other bit is can be understood from this plot. So what we did here was we took an offline data set, and that offline data set has enough coverage over state action pairs of the MDP. So as we saw in the offline RL lecture, If you don't have enough coverage over state action pairs, you will pay a price for sampling error because you haven't seen a lot of the parts of the MDP. So essentially what you'll do is you'll end up paying a price for outer distribution inputs. So here we assume that outer distribution inputs are not there because you've sampled the MDP sort of uniformly or sort of with a high coverage way. And what I'm plotting here is the x-axis shows the iterations of training. So I'm training a DQN or a fitted Q iteration style algorithm. It's being trained on the fixed data set. And what I'm trying to measure here is on the y-axis, I'm trying to measure the S rank or the effective rank of the features phi learned by my Q function matrix. So my Q function is this neural network that produces phi and then a linear weight matrix W that gives me the Q value. I'm trying to measure the rank of phi here. So phi is this matrix that has a dimension of state space times action space on one axis and dimension D on the other axis. So I'm trying to measure the rank of this matrix. And rather than measuring rank, I'm measuring the effective rank, which is a sort of surrogate for rank, as we discussed. Now, it turns out that if you measure this guy, you'll find that the rank actually degrades during training. So if you look at the grid world example, you'll find that the rank degrades. If you look at the Atari game, which is the asterisk game, you'll still find that the rank degrades. And if you look at some of the seeds which are shown as faint lines in that figure, you find that in some cases the rank drops down to super low values, such as maybe 10 or 15, something like that. And just as a point to note here, as a point of comparison, the value of D here is 512, and the size of the state space and size of the action space are super large. So they are very big numbers. D is 512. So typically the rank or the maximum possible rank or maximum possible effective rank that phi can have is 512. However, the values that we are seeing here are very small. They are like maximum or at an average 100 for the asterisk example, and in some cases even close to 0, close to 10 or something. A similar phenomenon exists in the online setting where again the rank drops, as you see on the grid world, where sort of rank becomes rank starts over from like 120 and goes down to like 40 or something, as well as in the case of online settings with more gradient steps, which corresponds to the orange line or the blue line, where actually you find that the rank or the S rank value drops down to super low magnitudes, as compared to when you have n equals 1, which is one gradient step per environment step. So that's the red line, which is the highest in terms of S rank. So what does this all mean? So let's connect it back to the statement on the top of the slide. So what we are saying here is when we are doing more and more gradient steps on the same data, which means we either have, which means that on the x-axis for the offline plots, the x-axis or the time step increases on the x-axis, and for the online plots, the larger the value of n. In those cases, we find that more gradient steps leads to a loss of expressivity due to excessive regularization, which manifests as a loss of rank of the feature matrix. So what we have seen so far is that when we do indeed apply more gradient steps, there is a loss of rank of the feature matrix, as you see in all these plots. And as we see on the next slide, this is really due to a loss of expressivity due to excessive regularization caused due to gradient descent. Just to summarize before we go down understanding what is this loss of regularization mean, the phenomenon that we are talking about here can be summarized in the schematic, where your feature vector phi k essentially decreases in rank as you train more and more. And this happens when you minimize TD error using your previous Q function as the target network. So that's summarized in this example. Why is this effect actually compounding, or why is this effect excessive over time? It's because what we are doing here is we are doing bootstrapping. So we are generating labels or generating the target values for Q function regression using a previous instance of the same network. So what we're doing here is let's go back to the original phenomenon that we talked about earlier with regards to gradient descent, where we looked at how gradient descent can give you regularized solutions, as we saw on this slide. Sort of applying this principle inductively over and over. So you basically are solving a sequence of supervised learning problems where your target labels are generated from your own previous instances of the network. And when you solve this sequence of supervised learning problems, in each problem you are accumulating some amount of rank drop because supervised learning imposes a regularization effect. And when you apply this over and over multiple times, what ends up happening is you pay a price for a compounding effect of rank drop, and that leads to a poor solution or a poor value of effective rank, as we see in these slides. So that's the reason why more gradient steps can lead to a poor solution, which is because your rank of the feature matrix degrades. And what does the rank of feature matrix degrading mean here? So imagine imagine what that actually refers to. So you had a hidden layer of size, let's say d dimensional, because that's what the dimensionality of the feature vector phi is. But when your rank is super small, such as for a d equals 512, if your rank is effectively 10, you are effectively using only 10 components of that 512 dimensional vector. So what you're doing here is you're not using your full capacity of the network to represent the Q function. In a sense, what that means is your Q function network is behaving implicitly as an under-parameterized network, which means you are not using your full capacity, even though you're provided that capacity to utilize. So what that means is, due to this excessive compounding effect of gradient descent regularization over time, which happens because you are regressing to your own previous instances, which is because you're doing bootstrapping, you might end up seeing a solution that is very low expressivity, because it is using only a few components of its feature representation, and that can be potentially a bad solution, as we'll see. So that's the notion of implicit underparameterization. And I'm happy to go over this in the class again if this is not unclear. If this is unclear from this video. So far what we have looked at is that implicit underparameterization is caused because of bootstrapping, because you are actually sort of regressing to your own generated target labels. So what we actually did was we actually verified an experiment where we conducted an experiment where we tried to verify that implicit underparameterization, or this rank collapse issue that we were seeing so far, is indeed caused due to bootstrapping. So it turns out that it doesn't happen when bootstrapping is absent. So when let's say you're trying to evaluate a particular policy, you can evaluate it in two ways. You can do Monte Carlo regression, so you can just say Q value is equal to the sum of Monte Carlo returns, which is sum of gamma to the t, RT, R of STAT, or you can evaluate it using fitted Q evaluation, which means you are doing policy evaluation using the Q function. So you devise a Bellman consistency operator, and you try to do QLearning style updates using that Bellman consistency operator. Turns out that when you do this fitted Q evaluation using the bootstrapping operator, you find that the rank drops way quicker than when you do Monte Carlo evaluation, where the rank is pretty much close to the ceiling, which is near 500. So that's a pretty interesting sign that that bootstrapping is a primary cause behind this rank collapse phenomenon. Similarly, this rank collapse phenomenon, what we show next is that it hurts the representability of the optimal Q function. So what we are trying to argue here is that the expressivity loss that we saw so far actually does happen with Q functions, because the effective feature dimension that this phenomenon gives us is actually quite small. So on the grid world example that we saw from the previous slide, where we also plotted the online grid world example, where we also plotted the ranks, where you see the blue rank is actually quite low and the red rank is somewhat quite high. What we found here was that it's actually hard to fit the optimal Q function if I were to regress on these features. So if I were to freeze the features and only regress to the optimal Q function on those features, it turns out that as you train more and more, as this phenomenon, as rank collapses more and more, it's harder to fit the optimal Q function, as you see on this plot, because the Q star fitting error over the features that are learned is higher than in the case with the red line, where the rank does not drop too much. And finally, just to sort of sum this up, rank collapse also corresponds to poor performance, as you can see on these plots, where the top row corresponds to the ranks, the bottom row corresponds to performance, where you'll find that performance is indeed kind of low whenever rank drops, or the performance is generally higher when the rank is higher, as you can see in these plots. With that, I'll end part 1, and we'll go on to part 2, which is distributions next.